So let's first do a very quick review of what we did in the previous lecture. Remember, in the previous lecture, we were talking about convex sets and functions. The reason those concepts are important is because convex optimization problems are a very special class of optimization problem. They can be solved in polynomial time. Okay, so the reason we talk about convex sets and how to prove a set is convex and how to prove a function is a convex function is because when you have your real-world problem, let's say if you have your chemical engineering problem, you do need to identify whether the problem is convex or not, right? So once you identify it's a convex problem, you can use the convex optimization algorithm to solve those problems. So if you have reviewed some papers written by researchers with engineering background, for example, I have reviewed some papers where people have a convex problem, but they are not aware of that they have a convex problem. So they use a non-convex solver, right? That's a very basic mistakes to make, right? Hopefully after taking this class, at least you can recognize whether a problem is convex or not. Okay, and we talk about different tools to recognize convexity. Two important concepts are the first order and second order conditions for convex functions, right? That's some tools you can use to identify whether a differentiable function is convex or not. And there are other very important concepts, things like operations that preserve convexity, right? If you cannot directly prove using the first or the second order condition, maybe you can refer to those operations that preserve convexity, things like perspective function or the max over a number of convex functions, okay? That's just a quick summary of what we did in the previous lecture. Okay, so in this lecture, we are going to talk about perhaps the simplest form of optimization problem. A lot of concepts in this lecture have been taught probably in your freshman calculus class. Okay, so here we are dealing with an unconstrained smooth convex problem. So you have a function of f of x you are trying to optimize. And the x are real numbers, right? So in this class, x is in Rn, right? And we assume this function is differentiable and convex. And we denote this optimal value of this problem as f star and the solution by x star. Okay, so that's one of the easiest problems you can solve in practice. And a lot of other optimization algorithms are built on unconstrained convex optimization. Okay. So I think I still owe you a very important property of convex functions. So we talked about in the previous lectures, for convex functions, local minimum is global minimum, but we never prove this, right? We just tell you empirically if you have a convex function like this, the local minimum is a global minimum, but if you have a non-convex function, for example, if you have a local minimum here, it's not the global minimum. So in this lecture, first of all, we are going to prove this property. Okay, so just to remind you guys, what is the definition of a local minimum? Right, we talked about in the previous lecture, but just to remind you what local minimum is. So we see x star is a local minimum if there exists delta greater than 0 such that for all the x in the neighborhood of x star, such that x minus x star, you can use any norm you like. For example, you can use the, let's say we use the Euclidean norm less than delta. We have fx greater than or equal to x star, right? So this is the mathematical definition of a local minimum we covered from the previous lecture. Okay. Then also to remind you what is the definition of a convex function. Okay, so by a convex function, the definition is the following. So if f is a convex function, then if we pick any x and y in Rn, then we have the following hold. If you take the convex combination of x and y, right, it is less than equal to the convex combination of fx and fy. Right, it's essentially this property, if you have a convex function, you draw a line at any 2 points, it's always above this function, right? Intuitively, it's like that. Okay, so now with those 2 definitions, we are going to prove this claim that if f is a convex function, then the local minimum is also a global minimum, right? So without loss of generality, let's just take, let's say we take x star to be as the local minimum. Right? So the claim is saying if x star is a local minimum, then it is a global minimum. In other words, if I pick any arbitrary, let's pick an arbitrary y, then if we can prove that fx star less than f of y, then we are done, right? So that is just another way of saying this claim. If x star is a local minimum, then pick any y in the domain of f, fx star should be less than or equal to fy. That's a definition of a global minimum, right? This is a definition of, so this is what it means to as a global minimum. Okay, that's what we want to prove. And in order to prove that, we are going to use the definition of the local minimum and convexity, right? Okay, first I'll recognize that since f is a convex function, we have this property, right? So now how about let's just take x as, in this definition, let's take, let's say we take x equals to x star. And y is any arbitrary y. Let's say it's an arbitrary point. Okay, and then we plug into the definition of convex functions, right? So the left-hand side, you just replace the x by x star and keep the y, right? So then we will get something as fx star plus lambda times y minus x star. Okay, so I did nothing but plug in the x star into this term. And I write it in this way. You will see that in a second why I'm writing it in this way. It's fx star plus lambda times y minus x star. Okay, it is clear at this point. Okay, and you can do the same thing on the right-hand side. It will be less than or equal to 1 minus lambda. You just replace x by x star, and then plus lambda fy. Okay. So now I have used the property of convexity, right? So next thing I'm going to apply is to use the property of local minimum, right? So x star is a local minimum. So by the definition of local minimum, let's just read the definition again, right? When x star is a local minimum, then for all the x that are very close to x star, right? If their distance is less than or equal to delta, then we have all those x has to be greater than or equal to fx star. That's the definition of a local minimum. Okay? And in this problem, we have a similar structure because you are perturbing fx star by lambda times y minus x star here, right? So if this number lambda is very close to 0, then this guy must be greater than or equal to fx star. Okay, say that again. So if, so let's say, if lambda greater than 0 is small enough, then we have greater than or equal to fx star. Okay, why this is true? Because fx star is a local minimum, right? If you pick a very small number lambda, which is very close to 0, it's like you perturb fx star slightly, right? Then it is due to the definition of local minimum, there must exist a lambda small enough. Maybe it's even much smaller than this delta number we pick, right? Then we can say this guy always holds. Right? That's just definition of the local minimum. Okay, in other words, we can, so let's deduct fx star on both sides of those inequality here, right? Then what we get is the following. Okay, so if you deduct the left-hand side by fx star, and you deduct the right-hand side by fx star, right? Then the right-hand side becomes lambda times fy minus x star, right? This is just very simple algebra. You deduct fx star on both sides of this inequality here, right? Okay, and then since we have this term here, we know that this is greater than or equal to 0, right? Because fx star is a local minimum, we already show that this guy is greater than fx star. And in other words, this term is greater than or equal to 0. And now we are pretty much done, right? So lambda is greater than 0. You can divide lambda on both sides, right? So this essentially shows that basically fy has to be greater than or equal to fx star. Then we are done, right? So since we pick y in a very arbitrary way, you pick any arbitrary y, then we show that fy must be greater than or equal to fx star. In other words, if fx star, x star is a local minimum, it must be a global minimum if function f is convex. Okay, so we are just using some very simple algebra and the properties of local minimum and convexity to prove this. Any questions here? Okay, so you can try to do the algebra yourself. It shouldn't be that hard. Now we have if you cannot read my handwritten notes, this is a cleaner version. You can read after class, okay? So that's this property we have not proved before. And here's another very important property for convex function. Okay, perhaps you have studied it. I'm sure you have studied maybe in freshman calculus class, right? Since I asked some of you this question in my first lecture, how do you really get the optimum of a continuous differentiable function. And some of you told me you just take the derivative, set it to 0, right? And in high dimensional, it's just take the gradient and set it to 0, right? Why this is true? We need a formal proof of that. Maybe you did one in your freshman calculus, but we are just going to do it all over again, right? So first of all, we are going to show first direction necessity. This is a necessary and sufficient condition, right? How to spell? Yeah, I think I spelled it wrong. Okay. So in other words, let's first prove that if x star is a local minimum, or for the sake of the argument, we can say it's a global minimum, right? Since f is a convex function, local minimum and global minimum are equivalent. So if x is a local minimum, how do we show the gradient of at x star must be 0? Any thoughts? You only need some argument from calculus in order to show that. Yes?
We use a Taylor expansion of f around x star.
Yeah.
And then we will come up with some inequality using the fact that x star is a minimum. We end up with the gradient being 0 for the inequality to be.
Yeah, that's a very good idea. But usually, if you just use the first order Taylor expansion, it still has some residuals, right? Because the first.
Take the limit.
You take the limit. Yeah. You can do something like that. Any other arguments? There are different ways you can argue that, right? The Taylor series expansion is a way of saying that. You just take the first order expansion, right? And then you take the perhaps the first order Taylor series expansion would be let's say if you expand at fx. Then that will be fx plus the gradient at x transpose the y minus x, right? That's like the first order Taylor series expansion. If y is close enough to x, you can only focus on the first order term, right? Because the higher order term will diminish faster than the first order term, right? That's something maybe you learned in calculus class. Okay, and a simpler way to argue would be let's say for the sake of the argument, if this gradient at fx star is non-zero, then there exists a direction that fx can decrease, right? So if you take direction, let's say the minus gradient direction, fx will decrease. Okay. And that's why fx star is not a local minimum, because there exists a direction you can further decrease fx, right? And why in this direction fx will decrease? You can argue this using the so-called directional derivative. Maybe just to refresh your memory, what is the directional derivative? Okay. So the reason you want to have directional derivative in high dimension is because in one dimension derivative is just a gradient with the derivative with respect to one variable. In high dimension, it's more complicated, right? If you just want to use a number to represent how does this function change with respect to a given direction? Okay. For example, you can define a direction. Let's call it d in Rn. Then the direction derivative using this on the direction d would be, you take the limit let's say h is a small scalar, h goes to 0, fx plus h times d minus fx divided by h, right? It's more like you want to perturb fx a little bit towards direction d, right? And then how will fx change? That's the directional derivative with respect to direction d, right? Okay, so anyone knows how to calculate this? What will be the directional derivative equal to? That's a very well-known result in calculus. It's nothing but the gradient of fx transpose d. Okay, so think about that. The gradient is more like the direction where fx will increase the most, right? If the direction is the same direction as the gradient, that is like the steepest ascent direction, right? If you take the negative of your gradient, then fx will decrease the fastest. Yes.
Doesn't like the magnitude of d have to be 1?
Yeah, you can take d to be 1. Let's say normalize that. Maybe yes, maybe that's true. The norm of d is 1, for example. Right? So that's why if you set d equals to the, let's say, negative gradient direction, then the directional derivative is negative, right? It's like the norm of the gradient, right? Then the directional derivative is the norm of minus the norm of gradient. Yeah. Okay. Then let's say if we set d equals to this, then this guy would be equal to minus the gradient transpose the gradient, which will be minus the Euclidean norm squared. Right. So remember that that's the norm thing we covered in the previous lecture. Okay. Yeah. So that shows the necessity why the gradient has to be 0. Right. If the gradient is non-zero, you take the negative direction, you always get a non-zero decrease in the function. Okay. Questions here? Okay, so now let's talk about sufficiency. Okay, so in other words, if the gradient is 0, we have to show x star is a local minimum. Oh, sorry. The gradient equals to 0. Okay, this is very easy to show from the result we got in the previous lecture. We just apply the first order condition of convexity. Okay, recall the first order characterization of convex function. I'm just going to write it down. The first order characterization tells us if fx is convex, then we have this fx greater than equal to fx star plus the gradient at fx star transpose x minus x star. Okay, and maybe you do not remember this formula, but geometrically what it is if you have a convex function here, you pick a point. Recall that the right-hand side is exactly the first order Taylor series expansion, right? At x star. You pick a point x star, and you approximate it by the gradient at a given point. Let's say if it's this line here. So the first order characterization means if you apply the first order Taylor series expansion at any point in the domain of fx, it always underestimates this function, right? That's what this first order characterization says. And now we know that fx is convex, and also the gradient at this point x star is 0, right? So this part will just all be 0, right, since the gradient is 0. Then this part will just be equal to fx star. And in other words, if you pick an arbitrary x, it will always be greater than or equal to fx star, right? The first order characterization is fx. The x is being picked arbitrarily. Okay, that's why x must be a global minimum, right? You are picking any arbitrary x. So you can say it's a local slash a global minimum. Okay. Any questions on this part? Yeah, so if you need a better handwriting, that's the slides we have, right? You can take a look. So that's the two main properties we want to prove before we talk about algorithm, right? Usually when you study optimization, you first learn about the property of those functions, right? Once you know the properties of those functions, you can come up with an algorithm, right? Some people turn to teach it in the other way, first teach the algorithm, then the property. I think the other way is better because after you learn the property, you can design an algorithm yourself to solve those problems, right? So those are the properties we are going to use to solve this problem. And in this lecture, we are going to talk about two algorithms to solve unconstrained optimization problem. The first is called gradient descent. The second one is called Newton's method. In a high-level view, the gradient descent will only use gradient information, right? It's like the first-order derivative information. In the second algorithm, we talk about Newton's method, which uses second-order derivative. In other words, the Hessian matrix of a function. So then I'm going to talk about the details of these two algorithms. So for gradient descent, as we have proved in the property, right? If the gradient is non-zero, then it's not a global minimum, right? So you will always, search along the negative gradient direction, right? If you search around the negative gradient direction, this function value will always decrease. It's like you are trying to going downhill to find the local minimum, or in other words, the global minimum, right? So the basic idea is shown here. You are just moving in the direction of the negative gradient at a given point, because this is the direction of steepest descent. Why it is the direction of the steepest descent? That is what we have already shown using the, where is it? Okay. Yeah, we have already showed that using the directional derivative, right? Why the negative gradient direction is the steepest descent direction is because of this formula of the directional derivative here, right? So if you pick D to be any arbitrary direction, the directional derivative, in other words, how fast this function will increase or decrease with respect to this direction, is being calculated as the gradient transpose this direction, right? If you want to get the fastest decrease, you should go on the negative gradient direction, right? It's like, suppose the gradient direction is here, and you want the steepest descent, you will always go to the negative gradient direction, right? If you pick an arbitrary direction D, it is not the steep descent direction because remember when you calculate the dot product, you need to, it's like the vector magnitude times cosine theta, right? There is this angle. If this angle is theta, you need to multiply the vector magnitude by cosine theta when you take the dot product, right? right? But if the angle is exactly the other way to the gradient, then cosine theta equals to 1, right? That's the reason this is the steepest descent direction. Okay, so that's the intuition of why we are doing gradient descent. Okay, and algorithmically it works as follows. If you stay at a point as xk, you will change xk along this negative gradient direction by multiplying a small number tk, right? So tk is called the step size at iteration k. Okay, some of you may did some machine learning research before. If you use software like TensorFlow or PyTorch and so forth, essentially what they call a learning algorithm is an optimization algorithm, right? So in TensorFlow or PyTorch, they do something called stochastic gradient descent. And there is a parameter called learning rate. So the machine learning people are very good at making up fancy names, right? It's nothing but the step size of going along the negative gradient direction. But if you find something called learning rating in those machine learning software, they are nothing about this parameter tk here, right? Okay. And the choice of the step size tk is really crucial for the convergence of the algorithm. If you fail to pick a very good step size, your algorithm will not converge. I will show a very small example later on. Okay. And upon appropriate conditions, it will converge to the local minimum or the global minimum for convex functions. Okay. So that's something I've already talked about, why the negative gradient direction is the steepest descent direction, right? So the proof is very simple, just 3 lines of proof, right? If fx is a differential function, then of course the gradient is denoted as this. And if you take the directional derivative of f in a unit vector, yeah, so Ari is right, we should pick a unit vector just for the sake of the argument to be fair, right? Because the magnitude does matter. So if you have the unit vector u, then the directional derivative f with respect to this direction u is calculated as the dot product of the gradient of f at x and u, right? The dot product is, this is equivalent to the gradient transpose u, right? You just take each element of the 2 vectors and multiply them, right? Hopefully with some familiarity of linear algebra, this should be very clear to you. Okay. And to find the steepest descent, we need to minimize the directional derivative. And this occurs when u is the opposite direction, and that starts proving that the gradient direction is the steepest descent direction. Okay, any questions here? This is essentially the main theme of any gradient-based optimization algorithm. You do want to take the negative gradient direction such that at least in the neighborhood of x, this is the steepest descent direction. Right? Okay, and intuitively, we can have this visual interpretation. So here, what we have is like a contour plot. Okay, I'm sure you have seen those contour plot before, maybe even in some geography class. Let's say if you want to go downhill, let's say around those corners, the function value is large, and then at this point, it is the global minimum value. If you take the negative gradient direction, it's like a direction perpendicular to this curve here, right? That's the negative gradient direction. That's the direction, if you want to go downhill, that is the fastest direction you can go downhill. That's just a simple interpretation. Okay, so here's another interpretation. It's a little bit more convoluted. Let me write it down so that you guys can slowly absorb it. So another interpretation is through Taylor series expansion. So let's say we do a second order Taylor series expansion of the function fx at a given point, right? Then we have fy is approximately fx plus the gradient at x transpose y minus x plus 1 over 2 Okay, so this is nothing but the second order Taylor series expansion. Okay, if you have already forgotten about that, take a look at your calculus textbook. Right? I'm sure that this is something, your calculus professor will keep covering throughout the semester. The first term is the gradient. The second order term is like the Hessian of this function fx. Right? So now how do we derive gradient descent through this second order Taylor series expansion? The way to think about is, since it's a gradient-based method, we do not really want to use a Hessian, right? The Hessian is more difficult to calculate than the gradient. But we do want to use something to approximate the Hessian. So in this case, let's say we just replace the Hessian by 1 over t times the identity matrix. Okay, why do we want to do that? It's a very arbitrary way of doing that, right? We don't know what a Hessian is. Let's just pick an arbitrary matrix to replace a Hessian. Okay, and there's no good reasons for doing that. But sometimes you can show very good properties by doing this very simple replacement. So if you do this replacement, we can get a first order approximation. So we will keep the first order terms. And then since we have the identity matrix, the second order term will be reduced to the following. Okay. Yes?
So quick question. So that first y minus x term, does that need a transpose?
The first...
Like in the 1/2 y minus x Hessian y minus x.
Oh, yeah, you are right.
Does
You
that
are
need a transpose?
Yeah, you are right. Good point. Yeah. Other questions? Yeah, so with this, we came up with this approximation of the function fy, right? So now the idea is that instead of minimizing fy directly, because that's hard, right? We are just going to optimize this approximation of fy. Okay? And what this is, we have fx plus a first order approximation, right? And how do we interpret this term here? Okay. The way to interpret this term is we want to set y that is close to x. So in other words, we are going to optimize this function instead of fy, right? Besides this first order term, this is like a penalty term, right? Because you do not want y to deviate too much from x, right? That's why you kind of penalize that by a quadratic term. That's a way to interpret that. So in the literature, usually people call this term a proximity term to x. to x with weight one over 2t. Okay. So as you can see, the way we construct this approximation is that we do have the first order approximation, but on the other hand, if y deviates too much from x, we give it a quadratic penalty. That's a way to think about this problem. And with that, if you try to minimize this function we constructed here, you will realize that you kind of reproduce gradient descent. Okay, so let's try to do it. Right, so maybe let's call this approximation, let's call it this, this approximation, let's call it f hat y. Right, let's call it this f hat y. So in order to get the minimum of f hat y, we can set the gradient of f hat y to 0, right? And the way to do it is take the derivative with respect to y. Then, this term is 0, right, because it doesn't contain y. And if you take the gradient with respect to y for this term, this is a gradient of fx, right? What you will get is the gradient of fx plus, what about this term here? It will be, it will be like, let's see what this is, okay. You can write it as 1 over 2t y minus x transpose y minus x, right? And take this gradient with respect to y. Okay. And that will be this guy equal to 0. I will do some simple calculation. You can check if my calculation is correct after class. So this will be 1 over t y. So minus okay. Yeah, so that will be the minus 1 over t. I think that would be x. Okay, and then you can rearrange this term and check y would be nothing but x plus x minus t times the gradient of fx. So exactly using this, you minimize this approximation with proximity term, we exactly reproduce gradient descent. Okay, and that's just a way of interpreting that. You don't really need to remember this, but this proximity term is used in the optimization literature quite often. Okay. So that's an interpretation in the slide. Okay. So the next question we need to talk about is how do we really choose the step size tk, right? This is a very important problem for gradient descent. So very naive strategy is let's just fix the step size, right? So here I'm showing the result of gradient descent for this very simple quadratic function. And if you use a fixed step size, you can see that these points will be jumping around. Okay, if we use a fixed step size. And after 8 steps, it doesn't converge. It kind of deviates from the global optimum here, right? So that's just a way of showing if you choose a very bad step size, things can go wrong, okay? So what about if you choose a very small step size, right? In the previous case, you can see things are jumping around because the step size is too large. If we choose a step size that is too small, it will have very slow convergence, right? Although you can see this trajectory is kind of leading to the global minimum, but the convergence is very slow if the step size is small. Okay, so that says there is always a trade-off in choosing the step size. If the step size is too large, it can deviate from the global minimum. On the other hand, if the step size is too small, then the convergence is low. Yes?
So wasn't that what, for the machine learning step, it was considered the learning rate, and that's a fixed, often it's a fixed learning rate,
Yeah.
Unless they do dynamic learning rates.
Yeah.
So why does it work in the machine learning optimization for to have a fixed learning rate if it wouldn't work even in this simple case?
Yeah, that's a very good point. Okay, I'm going to try to answer it, but maybe my answer was wrong. Okay, maybe you can ask some of the machine learning expert. Maybe some of the audience has a better answer than me. My conjecture is that first of all, in machine learning, you are doing stochastic gradient descent, not directly gradient descent. The other thing is that usually when it works, the step size is pretty small in machine learning. If you pick a learning rate of 1, usually that doesn't work in machine learning either. Empirically, I guess fixed step size do work for those machine learning applications. Okay, yes. You have something? No. Okay. Yeah, and also for this problem, the reason it doesn't work is because we are trying to create a very U-conditioned problem in the sense that you can see the coefficients of those x are different by 1 order of magnitude, right? Maybe in practical application, you have the same order of magnitude. That could be the case, okay? But maybe the explanation is wrong. Maybe some of the audience have a better explanation of that anyway. Okay, yeah. Yeah, so when the t is just right, you can converge in 40 steps. So that's a fixed step size strategy. The other very popular strategy in gradient descent is so-called backtracking line search. Okay, this slide might be overwhelming. Let me write it down very slowly. Okay. So the idea is the following. We can first choose a very large step size. And if it doesn't work, yes?
So for convergence, how are you trying to tell that we need to vary the step size with time?
Yeah.
And not keep it constant?
Well, for some problem, like what Zach just asked, maybe keep a constant step size will also work. But I'm just talking about a different strategy of non-constant step size. Right? In practical application, there are 2 ways you can do it. One is try different constant step size, see which one works. Right? If it works, you are done. If not, you can try some more sophisticated strategies like the backtracking line search I'm going to talk about. Okay? Yeah. So first of all, let's talk a little bit about the intuition of backtracking line search. Right? So first of all, let's think about why sometimes taking a larger step size wouldn't work. Right? Okay. So the reason is that if you take a large step size, the gradient may not be valid when you deviate sufficiently from x, right? So note that the gradient is taken at a given point x. Right? So when you deviate too far from x, this gradient is a poor estimate of the gradient at a different point, right? So in other words, so if you take x to the next point x plus, if x plus is close to, you would expect the gradient at x plus is close to the gradient at x, right? On the other words, if it is too far from the gradient of x plus will be, far from, right? So that's the intuition here. If you take a very large step size, you might be even going to the negative gradient direction, right? Because think about this case. This function is jumping around when the step size is too large. For example, if you stay at this point, if you take the gradient here with a small step size, you are still decreasing, right? If you take a too large step size until this boundary, you may be increasing the function value when the step size is too large, right? The reason is that if you look at the point close to the original point here, at this point, the gradient at this point should be close to the gradient at this point, right? But if you are going too far, for example, if you take this point here, let's say this point here, then the direction of the gradient at this point is a reverse direction of the gradient at your original point, right? If you take such a large step, okay? So that's the intuition. Okay, but on the other hand, if you are guaranteed to stay very close to the point x, then the gradient should still be valid, okay? So the line search is using this type of intuition. We have a condition to check if the gradient has a sufficiently decrease, then we know we are fine. Okay, the condition is stated as follows. If you take a step size t, and then if it is greater than this function value minus a value of alpha times the norm of the gradient, then meaning that you are overstepping. Because you know that when t is sufficiently small, the directional derivative is this guy, right? Okay, so this guy is so this part is the directional derivative of minus gradient, right? If your x is close enough to the original point x, then you are guaranteed to decrease by the directional derivative, right? If you go too far, it will deviate from that decrease. So that's why you can check this condition. If it doesn't decrease by alpha between 0 and 1 times the directional derivative, you know that you are deviating too far from x. And that's when you should shrink your step size by multiplying t by beta. So beta is a number between 0 and 1. Okay, that's the idea of the backtracking line search. Yes?
So it's basically like applying a first order Taylor expansion and seeing like if it's close enough to what is predicted by it?
Yeah, so the way to do it is that you first start with a step size that is large enough. Of course, you might be overstepping to a point that you do not get sufficient decrease, right? As you said, by first order Taylor series expansion, you know that if the new point is close enough to the original point, you are guaranteed to decrease by the directional derivative, right? If you know that it is not sufficiently decreased by the directional derivative, you know you are stepping too far. And then thus you should shrink the step size. That's the idea. Okay. Yeah, so that's geometrically how it works. Okay, you want to make sure you get a sufficient decrease. And here's the same example. If you apply the backtracking line search, it can converge faster. Okay. And then the other idea that is not very commonly used is called the exact line search. That means that you want to find the step size such that the function value is the minimum. But this is very hard to achieve, right? It is very hard to find the exact minimum of the step size, okay? But that's something called exact line search. Maybe for some special problem, you can do exact line search. Yeah, then we can talk a little bit about convergence analysis. Since this is not a very theoretical class, this is not a focus of the course. If you take the class in industrial engineering, they will spend a lot of time talking about how to prove the convergence order and so forth. One thing intuitively we can remember is that how fast does the gradient descent converge, right? The order of convergence, or the convergence rate, is 1 over k. K is a number of iterations. In other words, if you want to get epsilon optimal, then you need in the order of 1 over epsilon iterations. That tells you how fast gradient descent converge. Okay. Yeah. So now we can talk about the second part of this lecture. We did spend a lot of time on the gradient descent. But the idea would be very similar when you talk about second order method. Okay. So remember, in gradient descent, we are just using the first derivative information. In Newton's method, we are going to use the second order information to get a better convergence rate. Okay. So this is a formula of Newton's method. So instead of directly using the gradient, it is scaled by the inverse of the Hessian matrix. Okay. Now it is not very intuitive. Let's show how do we derive the Newton's method. Okay. Yeah. So the way to derive the Newton's method is exactly using the Hessian matrix and the second order Taylor series expansion. Remember, in the previous derivation, we were replacing the Hessian by the identity matrix, right? But now if you do not replace the Hessian by the identity matrix, we just use this second order Taylor series expansion, right? And with this second order Taylor series expansion, this part is a quadratic function of y, right? And you can get the optima of this function by setting the derivative of y to 0, right? I'm not going to do the algebra here, but you can take the derivative with respect to y. And then with that, you can find the y that minimizes this quadratic approximation exactly what is given by the Newton's method, okay? So this slide kind of shows you the difference to interpret the first order method and the second order method, right? The first order method is that you replace the Hessian by a proximity term, and you minimize this approximation. With the second order method, you are just going to use a Hessian, and you minimize this second order Taylor series approximation. That gives you the Newton's method. Okay, maybe spend a few seconds to absorb this slide here. Any questions here? Yes?
I'm sorry, can you explain why we're minimizing y again?
Oh, yeah, sure. So let's say you are standing at a point fx, right? But then maybe we can do a very local approximation of the whole space of this function, right? Let's just assume you are trying to find a y that minimize the function fy, right? But instead, we do not know how to directly minimize fy, otherwise we are done, right? So that's why instead of doing directly minimizing fy, we construct this approximation of fy using the second order Taylor series expansion, right? So the idea is that currently you are standing at a point x, right? You already know the value of fx because that's the point you are standing at, right? But standing at point x, you are approximating this whole function using a second order Taylor series expansion, right? It is an approximation of function fy, right? Then you are asking, what is the value that minimize this approximation, right? Okay, that's why you want to minimize y. So you can think about the x here is a point you are currently standing at. Y is any arbitrary point, right? You can. So now your question is, find me the y that minimize this. This is like a surrogate to the original function, right? Using the second order Taylor series. Okay. Yes.
Does the where it says it minimizes over y to yield x equals x minus everything, does it need like x plus or x plus plus to differentiate between?
Oh yeah. You can maybe denote this by x plus. Yeah. Okay.
So
X
it would
plus
be
is
x
a
plus,
yeah.
It would be just be x plus.
Yeah. So x plus will be the next iteration, or you can think about this x plus as the optimal y in this approximation. Okay. Other questions? Those are all good questions. Okay, so you can try to rederive this yourself after class. Okay. So there is an alternative interpretation. I will talk about it real quick. Okay. So remember that, the optimal solution is a point where the gradient equal to 0, right? So you can interpret Newton's method as a method of solving a bunch of nonlinear equations. Okay, so suppose we are standing at a point at x, right? And we want to find a direction v such that if you take the direction v, then the gradient at x plus v equal to 0, right? So essentially we are trying to find a solution where the gradient equal to 0. Okay. Maybe you guys have studied some numerical methods of solving nonlinear equations, right? So this is nothing but, n unknowns and n equations, right? You can use some numerical methods to solve those n equations. Okay. So the idea is that let's denote this function capital Fx equal to the gradient of Fx, right? So the optimization is equivalent to root finding in this case, right? Since because of the optimality condition, you are minimizing f of x, but it's equivalent to finding the roots of this function here, right? The gradient of Fx equal to 0. Okay, but for generic nonlinear function, it's very hard to find the roots, right? Maybe for some of the functions like quadratic function, you do know how to find the roots. But for generic functions, we do not know how to find the roots. So there are some numerical methods developed by Newton in the 17th century. It's a very old method. Okay, so the idea to find the roots of this function of Fx is you do a first order expansion of these equations, right? So Fx plus v is Fx plus, so this is like the Jacobian of those equations, right? So in this case, the Jacobian is a hashing of Fx. It happens to be, right? If you take the Jacobian of the gradient, right? That's a hashing of Fx. If you forgot about that, you can take a look at the calculus book. So with that, if you do the first order approximation of this equation, then you can rederive the Newton's method. Okay. So here we have a geometric way of interpreting that using one dimension. If you want to find the root of this function of f of x, supposedly you are standing at this point, right? The way to do it is you just draw a slope. And then once it hit this point, this is your new point. And then similarly, you can draw a slope again, and it hit this point. As you can imagine, it will converge to the root of this function here, right? So let's say if you draw a slope and then you hit this point here, and then you can repeat here. This is your new point at the function. you draw a slope again at this function, then you are going to hit this new point, and you keep repeating, right? At the end of the day, you are going to converge to the root of this function. This is a very naive way of trying to find the root of a function, okay? So I will talk about this real quick. This is called affine invariance of Newton's method. It's a little bit nasty here. You don't need to look at the details of those equations. I just want to talk about at high level intuitively what this is, right? So you maybe wonder, let's say if I have some variables I want to optimize. What if I do a linear transform or an arbitrary scaling of those variables, right? Let's say if you scale all the variables by 10, right? If you multiply all the variables by 10, would gradient descent or Newton's method give you the same trajectory, right? So this result is actually telling you that Newton's method is not sensitive to the scaling. You do not need to scale your variables if you use Newton's method. But if you use gradient descent, it is indeed sensitive to scaling. Okay, so in a very generic way, what it says is if you multiply the variables by a matrix A, so that suppose A is a non-singular matrix, you can take the inverse of A, right? So this is like you are trying to linearly scale the variables by the matrix A. And what this part shows is that the Newton's method will still give you exactly the same steps as you scale the variables linearly. Okay, but if you use gradient descent, it doesn't have this property. Okay. Yeah, let me skip this part. You can take a look of this after class. And similarly, if you want to use Newton's method, there are also things related to line search, right? We can just do exactly the same line search as we did in gradient descent, right? There's nothing special here with respect to backtracking line search. Okay, here's some results on convergence analysis. You don't need to read about this in detail. This is just to give you some high-level feeling about how fast those algorithms converge. The more important thing here is this here. When you look at convergence, the most important thing is how fast it converges with respect to the number of iterations, k, right? Here k is denoting the number of iterations, right? So the things we care about is that as k goes large enough, how fast does this error diminish? Okay, as you can see here, it is like a double exponential term here, right? It is 1/2 raised to the power of 2 and 2 raised to the power of number of iterations, right? And for gradient descent, remember, compare with gradient descent. It is in the order of 1/k, right? So that's how you can see that Newton's method has much faster convergence rate, at some expense, of course, right? This is it is not called double exponential convergence, but you can see the error diminish in a double exponential term with respect to k, okay? Yeah. And then what are the trade-off of first order method and second order method, right? First of all, if you look at the memory limit, each iteration of Newton's method requires n square storage, right? This is straightforward because you need to store the Hessian, which is an n by n matrix, okay? And each gradient descent requires O(n) storage, okay? And for computation, each Newton's iteration requires n cube flop operation, right? Because you need to take the inverse of a matrix, which is roughly n raised to the power of third. Okay. And each gradient descent direction is just a vector-vector product, right? That's why it's O(n) flops. And if you do backtracking, it will require additional O(n) flops pi per inner backtracking step. And Newton's step is not affected by Provenance conditioning, and gradient descent can seriously degrade if you have a problem that is not very well conditioned. Okay, yes?
Will we be talking more about conditioning?
No, we will just stop here because we do want to cover a broad topic. Yeah. Maybe we will talk about in the advanced topic of linear algebra towards the end of this semester. But for this lecture, we will just stop here. Okay. So the conclusion here is that, Newton's method has much faster convergence rate, right? It's the error diminished in a double exponential term, but at some expense, it has much more expensive memory and computation per iteration. That is exactly the reason why if you look at all the machine learning packages, none of them implement Newton's method. At least you never use Newton's method for solving your deep learning problem. All those are first order methods, right? The reason is that if you have a large number of variables to optimize, like a deep neural network, calculating the hashing is too expensive, right? Even taking you can try it real quick on your MATLAB, for example. Let's say if you have a 1,000,000 by 1,000,000 matrix, you can try taking the inverse of that matrix and see how much time it takes. Right? That gives you some sense of how expensive each Newton step takes. Okay. So having said that, there is another line of research. It is still a very active research area where people are trying to develop something called quasi-Newton method. The idea is instead of exactly calculating the Hessian matrix, we use some approximation of the Hessian matrix, right? But it's better than the identity matrix. So there are some methods trying to approximate the Hessian. For example, there are a well-known method called BFGS, DFP methods. People still regard those methods as second-order methods, although they are approximating the Hessian. In our homework, we will have a tutorial of the BFGS method. If you are interested, you can take a look at how BFGS works. The idea is we are going to use some sort of low-rank update to the Hessian matrix instead of calculating the Hessian at each step. All right, so here's the references, and then we have 2 minutes for questions. You can ask any questions, or I can talk briefly about the homework if you wish. Yes?
Cantor Newton's method guarantees convergence, but in some cases there might be looping during the iterations. Or if there's a looping, is there any way to prevent this kind of?
Yeah, so that would be you can use a backtracking line search as well to prevent that, yeah. Other questions? Okay, yeah.